Okay, so welcome back to the next session where we want to we left it at a very nice point, right? The previous video we left it at the end of gradient echo. What we were trying to do is we have a slice selection, we know how to encode the readout direction or the x gradient to obtain uh, how the signal, where the signal is coming from along the x direction. In the polar scanning mechanism that we showed before, we said you could apply x and y gradient and you could cover the u comma v space, right, with any theta that you want. So now what we want to cover is the second one, which is rectilinear, and in that if you have to do rectilinear scanning, you have to go to the negative axis. So we use the concept of gradient echo to show that we can go to the negative axis. What is still pending is how do you move along v direction. In other words, we did z gradient, we have used x gradient. So we need to separate it out in the y direction, or which transfer to v direction here. How do we do that? So again, so the frequency encoding provides the frequency encoding. When we talk about convention says we are talking about x gradient. The frequency encoding provides spatial information only along the x direction of frequency encoding. To reconstruct an image, however, we need to determine the spatial distribution of signal in 2 dimensions within the imaging plane. So we need to know, we know along x direction, we need to also know along y direction where it is coming from. So this we try to do. There are several ways to do it. One popular way to do it is using what is called as phase encoding, frequency and phase. This is again very with the line, if you have trained your line of thinking, right, for MR using the 2 other encoding schemes and the other concepts that we have looked, this is straightforward. Essentially what we are saying is, if you can combine this phase encoding with the frequency encoding that we already have, then we should be able to tell x comma y contribution, right? You know, within z gradient provided us the slice thickness or your imaging plane. Within the imaging plane, we talked about x gradient. If you combine phase encoding and frequency encoding, then we should be able to tell x comma y, which is your image. Okay. So let's look at what phase encoding is. So a magnetic field gradient, again we exploited GZ, we exploited GX, which was called as GZ was called as slice selection, GX was called as readout or frequency encoding. Now you are exploiting the other direction, GY. The magnetic field gradient is applied in the remaining direction. In our case, it is GY. Importance is when you are applying it. You are applying it after excitation. If you are applying it with excitation, that is what you did for slice selection, selective excitation. So this is done after excitation. But after excitation, during data acquisition, you did frequency encoding. So this one comes just before that. So this comes in between. You have the RF excitation, Z encoding, and before you start X gradient, you have to apply your phase encoding. Okay. What happens if you do that? Same concept. If you apply a gradient, right, gradient in your magnetic field, then the gradient is going to have a spatially varying phase shift to the spins. Okay. So now after you impart the if you disturb the phase shift, you give a deliberate phase shift in y direction, that is from one end of the y axis to the other end of the y axis, you have everything is at different phase. Now during subsequent data acquisition, you are doing frequency encoding in the x direction, right? So all the spins are now going to precess according to their frequency encoding, right, along the x at a particular x location. Along the y, everything is going to have the same frequency of precision, but then each one will be at different phase. Okay, so this is the idea behind phase encoding. To put it in picture, this is how. So this is a picture of time axis and what happens over time for a given y-axis. So if you notice at the beginning in the y-axis, when you have a volume, you have a signal. So every voxel in this plane is having same Larmor frequency, okay, and everything is in phase. Now just about when it fell on the ground, right after your excitation, now I am applying a gradient in the y direction. That means what will happen in the y direction, one end, right, now everything is in the same phase and same frequency. If I change the gradient, what is going to be, if I apply a gradient, one end will have higher field strength compared to the other end. So there is field strength is changing. What happens if the field strength is changing? Oh, it is going to start to precess slightly slow or slightly faster. When it is going to slightly slow or slightly fast, what is going to happen? Everything was in phase. I'm making some guys slow, I'm making other guys fast. That means the phase is going to change. But I switch off the gradient, right? So when I switch off the gradient, wherever it went out of phase, it is now going to precess at whatever field strength that is experiencing. Right now there is no other field strength, right? Only the basic whatever you applied is there. So it is all going to precess at the same frequency, but in the y direction, one end will have a different phase compared to the other end, and it is linearly changing. So each one will have, that is what this is saying. When you start with, everything is having the same phase, same frequency, same phase. Now I apply phase encoding or the gradient in the y direction. As long as the y gradient is on, I will change this phase. This becomes slow, this becomes fast. So this is where it is. So I am deliberately inducing this phase change. When I switch off, it will remember that position, that phase, and each one will precess at the same frequency that it is expressed, the field strength that it is exposed to, proportional to the field strength it is exposed to. So now along the y direction, even though the frequency is same, each one is at different phase. Now if I apply x gradient, right? So along y direction I have phase difference but same frequency. If I have x gradient, along x direction there will be frequency encoding. Along the y direction I will have phase encoding. So I can exactly tell from the phase and frequency analysis where the signal came from. Correct? So this is my y direction. I apply gradient just before recording. So more importantly, we want to put everything in the terms of sequence, right? So no issues here. I did RF, I do slice selection, that is your Z gradient, refocusing, I get my signal. But notice I am not recording the signal yet. Before recording the signal, I am applying a start of data acquisition. Before start of data acquisition, so this we did before. We acquired signal and then at the start of data acquisition, we applied a gradient. Instead, we are now just before start, just after here, applying a phase Y gradient for short duration. A short duration, when I did this, what happens is each of the phase is different. Now I apply the same X gradient. So I have differentiated the Y direction, I have differentiated the X direction. That is from the volume. Now my signal that I am recording can be distinguished from X and the phase, or the frequency and the phase of the signal will tell me where it is coming in X comma Y. Okay, this is my data readout. How do you put this in terms of our vector, your spatial frequency domain representation? This is same as A before, right? I am applying Y gradient, no Y, no Z gradient, no X gradient. If I apply only Y gradient, I will have only Y frequency component. I will move A here, right? That's what we did. When we applied only X gradient, no Y gradient, it moved along U direction. If I have Y gradient, no X direction, it will move along V direction. Very straightforward, nothing new. But the thing is, I am not recording any signal. I am applying X gradient now. If I apply X gradient and read out, I am starting from here, I am reading out. So now we have seen two cool things. Not only can we go in the negative and start using gradient echo, I'll start from negative axis. I can use Y gradient or phase encoding to move in the V direction. So what happens when we combine these two? We should be able to cover the rectilinear space, right? So what is the signal? Phi y is the accumulated phase for the duration over which you are applying the phase encoding. Gamma gy tp and wherever it is at y. So it is gradient is applied along y direction, right? Gy y. So this is the maximum phase will be gy tp y. Okay. So your phase is given like this. So how does your baseband signal change out? Your baseband signal same as before. Only thing, x is varying with the t readout direction. In your y direction, you have this phase information. So if you have to recognize this, you'll quickly recognize this is also a Fourier transform. If you make appropriate variable identification. So your u is gamma gxt as before. Your v is gamma gy tp. Right. So essentially, what you have recorded is a Fourier transform data corresponding to this frequency u comma v, right, along the direction that was shown in the previous slide. So we can combine, right, you combine your gradient echo and your phase encoding. We can travel to the negative axis and move up and down in the u. So this is the pulse sequence. RF excitation, slice selection, refocusing. I am not recording the data, so ADC is not your free induction decay here. Rather, I am applying a phase encoding. Just after that, I am doing a frequency encoding and I am reading out the gradient echo during the frequency readout encoding, right? How this translates to our diagram here in the space? By doing this one experiment in this one sequence, we are acquiring data. So A is moving it in the V, here B is moving it to the negative axis. My readout therefore starts at the negative axis and ends at Gx tau, whatever time duration over which you acquired Ts, gamma is the highest frequency over C. So one gradient pulse echo sequence will give you one line like this. You have to repeat this experiments to get different lines. Your A could be different each time, right? Therefore, you will get parallel lines moving around. Clear? So let's also complete, right? The same token we talked about gradient echo. We will also talk about our pulse spin echo that we did before and how to represent that also in this sequence diagram that we have built to communicate. So recall previous pulse sequence that we have done so far is free induction decay or a copy of the free induction decay due to the gradient echo, not due to spin echo which we covered before. So the signal experiences whatever we have covered so far, the signal actually experiences T2 star decay. Remember what I told you in the last lecture or the previous one. That's a fundamental. The echo, gradient echo, your dephasing happens because of change in magnetic field. Therefore, it is related to T2 star. Whereas in spin echo, we recognized it is due to spin-spin interaction. Right? It is not due to change in magnetic field. It is due to the material property. So, to measure spin echo, that is, we want to do T2 decay, we need to apply a 180-degree pulse. Recall our sequence that we did before, or the sketch that we showed before. Before we do the timing sequence and see how it travels the frequency space, recall this is what we did. Pi by 2, you allowed it to dephase, and then immediately you applied 180-degree pulse, and then it starts to come together, and you flip to this many times to get what is called as spin echo. So how do we write the spin echo sequence? Okay, so nothing changes. So RF is same. You do 90-degree. You do the slice selection. So you have picked your slice. No, nothing new here. Once you pick the slice selection, you are getting some signal, right? When you do the slice selection, you are getting the signal, but immediately I am applying phase encoding, but I am not recording the signal. I am applying the phase encoding. The moment I apply phase encoding, I start by frequency encoding. However, I am not, if it was just recording the signal, right, then this is good enough. I would have recorded the signal. With phase encoding, frequency encoding, I would have got the signal. But this is not what I want. Now I am applying 180-degree pulse. It starts to dephase. Quickly thereafter, I am applying 180-degree pulse. What this 180-degree pulse does is it groups the signal together. Alright. Now, once I do that, it will take some time, right, for the signal to regroup, right? It is dephasing. I apply excitation again, but I apply it so that it is 180-degree shift. So when I do the 180-degree, it starts to regroup. So there is, after I apply this, there is some time it takes before which, and then the signal starts to form back echo. I am actually measuring this echo. While I am measuring this echo, I have already imparted phase. I am just doing frequency encoding. So I am measuring the echo that is due to the spin, and therefore this is a spin echo sequence. So the data that you are recording is an echo due to the spin. So it is called a spin echo, and the signal is related to T2, not T2 star. That is the difference. So how do we look at this in the diagram in UV? I started applying the signal, but I am not measuring it. So 2 allowed me to do phase encoding, meaning moving in the Y direction. Once I moved there, in 3 I should have had signal, right? But I am not measuring the signal. So the 3 regular, it is doing signal, but I am not measuring it yet. At 4 I am applying 180-degree, meaning I am flipping. So when I am flipping U and V, it will come here. So essentially I am at this location. Whatever signal that I am going to record is going to have minus U minus V as a starting location here, and then record until your TS, right, for the period of TS along the readout direction, which is U. Clear? So what we have seen is even our spin echo can be represented using the sequence diagram, and I should know how to represent it as a coverage in the frequency domain. So clearly what we have done so far is for one sequence. If you have to cover the whole UV space, I have to repeat the sequence. Therefore, it becomes important. We kind of complete what are the important aspects for pulse repetition. So to scan different lines in the frequency space, you need to repeat the steps. You can cover it with rectilinear way or using polar scan. Okay. But you have to wait for a period so that it all comes to the signal origin. Right. So if it is slow imaging, no problem. In slow imaging, you wait for a long time so that TR is far greater than T2. MXY is completely disappeared, you apply that. So in slow sequence, whatever we covered, you just repeat. But that might not be the case for fast imaging sequence. When we do fast imaging sequence, what happens is you are already doing multiple spin echo, right? You have tried to get your signal as fast. You don't wait for the multiple. Otherwise, remember, you have to wait for it to go back to equilibrium and then repeat the exam. So we don't want to do that. So spin echo, if you want to do fast sequence, you do multiple spin echo. But the problem is, I want to do it faster. That means I don't want it to naturally dephase, which it takes so much time, right? Dephase and then it comes spin lattice interaction, your T1, it comes to equilibrium. If I want to do all this, if I want to repeat the experiment multiple times, that is select the same slice, apply different GX, GY, same Z gradient, apply. I want to do this repeat several times. I want to have a better way of losing the signal from one acquisition before I start the next acquisition. So what can we do? We will do what is called as, whole idea is I'm getting the signal from Z, from a volume, right? From a slice thickness. How did we do that? We applied a Z gradient. Not only that, only you apply Z gradient, you don't get signal because it is all cancelling it. We applied a polarity switcher for a short duration. So we made what is called as refocusing pulse in Z gradient. Why did we do that? When you do the refocusing, it will focus back and the signal will start to appear. Now what I want the signal to, the coherence to go out. I don't want them to come together. Then what will I do? Apply another Z pulse so that you accelerate the dephasing, right? So you spoil the signal before the next signal. How do you spoil the signal? In the volume, whatever is coming. If you don't get anything from the volume, there is no point in X and Y, right? So I spoil the signal. How do I spoil the signal? apply a Z gradient. We got focusing pulse by applying a Z gradient. Now apply another Z gradient, you will spoil the pulse. So spoiling MXY prior to subsequent excitation is an important step. How do you do that? Is applying what is called a spoiler pulse, or spoiler in this sense is a Z gradient. Okay. So it will deface the entire slice volume that you have. So now let us look at updating our pulse sequence diagram to be more realistic, including representing how we put a pulse repetition also in the diagram. Okay. So here we will start to call the sequence that we have seen. We'll see again, but now we will call it a realistic pulse sequence. This missing link, we need to look at this and see if you have understood what this fill in the blanks is. Okay. So here we start with RF. You do the slice excitation like before, but there are 2 or 3 important points that I would like for you to pay attention to why this becomes realistic. Notice when we showed our in the previous pulse diagram, you would have noticed only rectangles. That is, the gradient is on, it goes from 0 state to the highest Gx or Gz without any time gap. In reality, there's a slew rate, right? So in reality, it is going to take some time before it reaches. So in the previous sequence that we showed, it was all ideal. That is, turn on means it goes from 0 to maximum instantaneously. Likewise, it drops from maximum to 0 instantaneously. Realistic means I am now saying now it takes some time to go up, it takes some time to come. So all the rectangles became trapezoid. That is one form of realism that we have incorporated in explanation of this diagram. Okay. Then what you notice is each of the slice selection, after slice selection I did gradient, Y gradient. After Y gradient I did X gradient. Correct? And then I had a switch here. But then notice now that I have essentially put everything about the same time, right? I am switching my Z gradient, I am switching on my X gradient, I am switching on my Y gradient almost simultaneously. Yeah, because your signal of interest is all happening rapidly and it's all happening simultaneously, right? So you don't want to waste time. So essentially for all practical reasons, they apply all of them near simultaneously. So that is also explained here. So that is making it little more practical. Realistically, that's what they do. And then one another thing that you see is you just saw one rectangle and shaded area, right? Now what you are seeing is parallel lines here. What are these parallel lines? These basically says that we are repeating this experiment each time different value of gy or gz, right? Of the gx. So varying gy in each cycle. So we are saying that by putting this hash line, we are saying that each time we are repeating the experiment with a different value of the gradient. This is a new guy. So this is for one sequence, you repeat the sequence multiple times. So we have put a breaker here, the time axis, and said we are repeating the next repeat sequence starts. So you are repeating this. So we have incorporated repetition also in our pulse sequence diagram. Now when we talk about pulse sequence, just before you repeat, we talked about including a spoiler gradient, which is Z. So the spoiler gradient each time is at different values just to spoil. So now this is a realistic sequence where we have made it clear the realism with respect to slew rate, realism with respect to starting times of application of the different gradients, realistic with respect to showing the repeat time, and also showing that each time you repeat with different gx gy value. All of this full process is vividly explained, right, in form of a diagram, which is pulse sequence diagram. This I would expect you to also understand in relation to how you are able to travel the Fourier space. This will be the art. If you understand this, this is the scope of the lectures. I would at least like for you to understand the sequence. Given the sequence, you know how to tease out and understand where you are moving in the UV space. So for example here, one is Z selection. 2 is I am applying Y gradient, so I am moving in Y direction. And then 3 I am applying x direction also, right? In 3, I am doing read out x gradient. So 1 is z gradient, 2 I am moved in gy. Of course, here you are assumed, I mean, just to demonstrate, this is one of the lines, right? You have repeated the line, so you got one of the lines, you are moving to, you are moving here, and then immediately thereafter you are applying gradient and reading out. So you are starting from here, you are reading out. You repeat this for different v, right? You will have different lines. So this explanation you should be able to do. Last but not the least, did you get a chance to realize what this should be? Okay. So realistic, what sequence are we talking about? Straightforward. Pay attention to the detail. What is the signal I am reading? It's an echo signal. So it has to be some sequence with echo. In the echo due to what? Oh, I don't see 180-degree pulse here. The echo is coming. Previously, I know if there is 180-degree, then it is spin echo. Now I see a echo, but this echo is coming because of gradient switch. So this is a gradient echo. So a realistic gradient echo pulse sequence. So can we do the same exercise for the next sequence? Can you recognize what this sequence is? Well, everything else is same as the previous slide. What is different here is, you see here, this is the echo signal that you are measuring, but in the echo signal I have 180-degree pulse. Therefore this echo is spin echo. Everything else is same, right? Realistic spin echo pulse sequence. I hope you will do the same exercise of seeing how 1, 2, 3, how you go here. Do you understand your travel path? This is something that you need to repeatedly do to get your own appreciation. Okay, so now what we will do is, last but not the least, can you again do the same exercise? This should be fairly straightforward, right? Oh, I see this. I should have not shown this perhaps. Maybe that will be the task in the exam or homework, right? So the idea is, look at the sequence. Can you guess the path? Look at the sequence. I have RF pulse, but I am applying X and Y simultaneously along with slice selection. Right? So I am not having a gap. In the readout direction, I have both X and Y on. That gives me the clue that if X and Y are on simultaneously, it has to be a polar. Okay. So this is a polar sequence. Of course, it's also polar, but echo is due to spin. So realistic spin echo polar pulse sequence. Clear? So I would like for you to go over this again and again. Try to see if you understand basic sequence and how do you represent. If a problem is given in English, description is in English, and they tell you this is the sequence, I want you to realize, can you draw the pulse sequence representation of it? Can you show how the data is acquired? These two are the take home. If you understand these two, then you have understood the physics, then you have understood the data acquisition scheme, right? Then reconstruction is not a big deal. So to summarize the data acquisition, we covered design functions, magnets, gradient coils, all those things. We also covered the gradients pulse sequences. And then we talked about slice selection is usually Z gradient, and then the forms of scanning, rectilinear and polar scanning. Okay. We also made distinction between your T2 star, which is your dephasing due to change in magnetic field, and spin echo, that is due to your spin-spin interaction that will come in your spin echo machine. All this time we have repeated several times, so I hope you get this. But critically, I would like for you to pay attention to the last three. That is the most important take home that I want you to understand from this module, which is, you should understand the purpose of each pulse. You have pulse sequencer, right? Each of the pulse you should understand the physics, what the aspect of the physics that we understood this pulse is exploiting, and therefore the signal is having the contribution. It is always f of xy. Physics gives the meaning for this f of xy. So can you see that? Second is the relationship between the pulse sequence and the trajectory in the Fourier domain, right? The 1, 2, 3, 4, right? Polar sequence or rectilinear, how you know that sequence. I would like for you to connect between the pulse sequence diagram and the trajectories in the, that you need to understand. Of course, last is difference between your ideal and practical pulse sequence, right? This I think you should. These three are very critical. If you understand that, MRI is, you will understand why people rave about MRI as being a be all end all modality. So last but not the least, you should understand this very important concept of the signal that you are measuring, S of t, right? It is very counterintuitive. I'm saying S of t, we are always trained to think about a time domain signal. It turns out S of t here that you are measuring, or S0 of t, which is your demodulated signal, is actually measuring the Fourier transform of the signal. Okay. So more the time you allow, more the frequency content you capture. You can think about it that way. So you are actually capturing the Fourier transform of the object. F of xy is your object. You are capturing, you are measuring the Fourier transform of the object when you are actually measuring S0 of t. Once you have that, basic image formation reconstruction is straightforward, right? This is the important aspect. So relationship between f of x comma y and the imaging properties. That is, the f of xy, we showed this pulse proton density, but we have already covered in physics how you weight the basic different time sequence of acquisition to different properties of T2, T1 weighted image, right? Same thing you have to be able to explain. So you should understand the combination and how you realize that combination using the pulse sequence diagram, and how you understand from the pulse sequence diagram the Fourier space, or the Fourier space how you have traveled, and therefore your S0 of t. Okay, we'll stop here. So what we need to still cover is, from here it is little straightforward. From here what we need to cover is, I have the data, how do I get my image, right? You know, inverse Fourier transform. So conceptually, you know, from here everything you should be able to, nothing should look new. We'll just formally complete it, but from now, image reconstruction should be a cakewalk if you understand this, because we have done this for CT. Here we have understood what we are recording, which is Fourier transform of the object. So I should be able to go back to the object or the image. I should be able to obtain the image. Then we need to talk about the image quality. Okay, so maybe another 2 lectures we will be able to complete the syllabus. So we'll stop here for this module. Thank you.